All right, so we're going to do a little worksheet. Well, not a worksheet, just a little exercise today. We've talked about the basic design methods for control system design, the classical methods. They are the frequency response method, where you work on Bode plots, and also the root locus. And both of those diagrams show up in SISO tool in MATLAB. Today, what I want to do is do a similar type of problem, but without using those types of equations, without using the geometry. We'll do it. Today's entirely an algebra day. So we'll have a lot of algebra equations come up, but we can show that we can solve the same problem, if it's not too difficult, to use algebra. So what you have in front of you is a picture of a communication satellite. This is typical of something that we would use for like DirecTV, if you have satellite TV. So you got an Earth station, that's beaming information up to the satellite, and it's got to be in the right place in its orbit in order to cover the United States, and it sends information back down to us, and we're happy when we get our DirecTV. Similar types of things are put. There's a constellation of these up in space for GPS, so you know where you are from your cell phone because you are picking up GPS signals. And today what we want to do is we want to make sure that the satellite is pointing in the right place, pointing in the right direction. And what we want to do is pretend we're trying to do a pointing control problem. Okay? Now, the satellite in real life has to deal not only with pointing, but also has to deal with its north-south position. We don't want it to drift, too far down and then be covering those people in South America, or too far up and covering those people in Canada, where aren't there many customers. We want to make money and keep that thing north and south pointed at us, and of course east and west pointed in the right direction, because we don't want to be beaming entertainment out into the Atlantic Ocean. So let's consider that we're basically trying to control this angle, theta. Pointing control, theta is the angle. We want to control the angle. And so the basic differential equation, up in space, there's practically no friction or anything like that. And so we can say that from Newton's law, from Newton, we have this idea that theta double dot, angular acceleration, is equal to the torque. Okay, if you wanted to turn this thing, you have to twist it, and twisting implies you have to apply torque. Okay, it's just like taking off a nut on a bolt. You have to twist it, and twisting force is what we call torque. That's why we have things like called torque wrenches. And let me call this torque. Let me give it a name. Again, I'm trying to think of a letter that's not already used in some other thing. Let's just call it the torque. Let's just call it U. Okay, U is the input. Okay, so if we take a look at the transfer function now, the transfer function we can think of it as something that goes in this block diagram. This is kind of going all the way back to the beginning of the semester. We're controlling theta here, and the input is U. And so this is, if we did the Laplace transform, basically our model looks like this: 1 over s squared. Okay, 1 over s squared. If you did the Laplace transform of this and did theta of s over u of s, you get 1 over s squared. Now, our goal today is to try to do a pointing control. And so let's imagine this is now in a feedback system. So our process is 1 over s squared. And here's theta. And what we're going to do is we're going to compare it to a desired angle. This is the reference angle. Let's call it theta r. This is the reference. And then what we're going to design today is we're going to design a compensator. We did some examples of lead and lag, and today I think I'm going to let's do a lead compensator, and the compensator will be of the form K S plus Z, a 0, we have to design it. And then there's a pole. I'm just going to arbitrarily just say it's, just pick a number, say 5. So this is a phase lead compensator. Okay. Now let's sketch the root locus diagram and see if this thing is somewhat a reasonable idea. So let's take a look at the root locus diagram. And so we set up our root locus diagram, and we'll call this the real axis, call this the imaginary axis. And so we have to sketch everything that we know in the open loop. The open loop now has a couple of poles right here at the origin. This is the process. And then we have a pole out here at -5. This is due to this factor. And then we have a 0. We don't know where it is. Okay, so I'm just going to arbitrarily just say it's right here, and the pole's at -z. Okay, let's sketch the root locus. The root locus, let's do some. We got a handful of little rules that will kind of give us a rough sketch. We have basically 3 loci because there are 3 poles. The poles, the branches need to start at the x marks. There's 2 x marks here. There's 1 x mark here. One of the loci must end up on this, and 2 of them must go off the page. So we have 2 asymptotes. And so they must look something like this. Okay, some dashed line. But we don't know where to put it. We can't calculate the location. We can't calculate the location of this. We don't know it because we don't know this number here. But we do know that 2 of the loci will go off the page, and 1 of them will go to the 0. Another rule we could apply is to take a look and see where on the real axis there may be loci. So you would stand anywhere on the real axis and look to this direction, look to the right, and we see an odd number of loci, we should color in that part of the real axis. And if we do that, we see this part should be colored in. Okay. So a possible root locus is that this thing looks like as k increases, one of the closed loop poles moves this way, and the other closed loop poles, go off the page. So maybe it does something like this. Okay. And so this suggests that the closed loop poles, which lie on these curves, are all in the left half plane, and this should be a stable control loop system, stable closed loop, stable control system. Which means we should be able to get our satellite to point where we want, and it should settle out. Okay? So now we have 2 parameters that we want to design, k and z. Okay? So let's pretend let's figure out that we a potential specification. Here's the design specification. Okay, the design specification is going to be a specification. In this case, it's a time response. It's in the time domain. We're describing the time response. And so maybe one of the things we would say, I want this satellite to settle in 10 seconds, 10 units of time. And then maybe we may also say overshoot less than 10%. Okay. Now what we have to do is we have to take this information and say, what does this mean in S domain? Okay. Translate this information into S domain. We're doing S domain design in this class. Okay, continuous time, Laplace transform. So for example, let's take a look at the settling time. Settle in t, the settling time is equal to 10. Settling time is equal to 10. And that implies for us that the time constant time constant, let's assume that we're settled in, within 2%. We want to settle within 2% in time and 10 time units. So the time constant should be approximately 10 over 4. That's 5 over 2. That's 2.5. Okay. So that's the time constant. So if we know the time constant, then we know what the real part of the second order poles would be. This is the process looks like a second order. The overall system is third order. But then for a second order approximation, second order approximation, we have that S star is equal to the real part of S star plus J times the imaginary part of S star. This is the desired closed loop poles. Okay, the desired poles we're going to call it S star. Okay, and this part here, this should be 1 over the time constant. Okay, 1 over the time constant. So 1 over the time constant will be equal to 0.4. Okay, so now we have this number. We can use the overshoot specification to get a second number. Okay, the imaginary part. All right, so let's take the overshoot. We remember an overshoot equation for the second order approximation is e to the minus the real part of S star divided by the imaginary part of S star. And somebody's going to have to pull out a calculator here because I can't do exponentials in my head. And we have to multiply by pi. And that should be, we said less than 10%, so let's set up the equation for 10%. 0.1, okay, 10%. Let me write it this way, 0.1. So we have minus the real part of S star over the imaginary part of S star times pi is equal to the log, the natural log of 0.1. And I'm looking for the imaginary part here. So I get the imaginary part of S star is equal to minus the real part of S star. And there's a pi, don't forget that. And then divide that by the log of 0.1. So maybe somebody can plug in this for me. The real part of S star is 0.4. So I get minus 0.4 pi divided by the natural log of 0.1. Okay, so somebody plop that into your calculator and tell me what you get. Roughly a half? Okay, let's say it's a half. Approximately 0.5. Okay? So we've done a bit of work. Basically, all this work on this screen is basically taking time domain information, settling time, overshoot. Okay? We're taking time domain information and converting it into these S domain numbers. You know, it's something that we as electrical engineers would feel very comfortable with. And so the upshot of it all is we translated everything and we say that these time domain specifications basically say that a second order system, a second order approximation would have poles at S star is equal to negative 0.4 plus or minus J 0.5. Okay. So this is one of the skills that we carry away as electrical engineers graduating from Auburn, is that we can take time domain information and translate that into some sort of funny numbers, some complex numbers. Okay? So that's kind of the amazing thing of engineers. We use complex numbers to deal with things that, would look like that. All right, so what does that mean? What does this number mean? It means that in our satellite pointing root locus, we hope that we want to put this number right here to be at negative 0.4 plus j 0.5. Okay, so that's the root locus problem. The root locus problem says that we're going to put negative 0.4 plus j 0.5 right here. And we're going to do it by doing two things. We have to adjust z. We have to find the right z so that the picture flows right. And then k picks a point along the curve. So we have two unknowns and two equations. Okay, today we're not going to use the angle criterion and the magnitude criterion because it involved a lot of trigonometry. Some of us learned trigonometry, they claimed, in the 7th grade. And I said I didn't learn it until I was a senior in high school because I went to a backwards community. We're going to go even further back in our education, and we're just going to use algebra today. Okay, so we're going to use an algebraic approach to solve this problem. Let's try to solve this problem algebraically. An algebraic approach to the solution. Okay. So let's take our block diagram again, and let's figure out what describes the model. Z is unknown, k is unknown. We've got an s plus 5. We have a 1 over s squared. Okay. And we know that the closed loop characteristic, well, let's review even further back. Let's just go all the way back to the beginning of this semester and say this is theta and this is theta r. So we have theta of s over theta r of s. This is the closed loop transfer function. The closed loop transfer function is the forward gain divided by 1 minus the loop gain. And the loop gain in this case is a similar function. Okay. This is a 1 down here. If we had something else in the bottom, we'd have to include that as well. If we had something in the feedback path, we have to include that as well, but this example doesn't have that. This minus sign is going to cancel out this minus sign, turn it into a plus sign. And we're going to clean up the algebra a little bit, and we get k s plus z on the top, and in the bottom, we're going to get s squared s plus 5 plus k s plus z. Okay. We are studying the closed loop poles, so we need to focus on this. This is the closed loop characteristic. That's the closed loop characteristic. Let me clean up the algebra a little bit. So we have s squared times s is s cubed. S squared times 5 is 5s squared. I have ks, and I have a kz. Somebody be checking my algebra, okay? I have to write and talk at the same time, and that's challenging. Okay? Now, we want, is this okay? We're all right? All right. Now, we want a pair of poles at S star is equal to negative 0.4 plus and minus j 0.5. Okay. So that means this characteristic equation, therefore, the characteristic is equivalent to, it must have a total of 3 factors. It must have something like this. S plus 0.4 plus j 0.5. It must have S plus 0.4 minus j 0.5. And it must have S plus some number that we don't know. Let me see. I need to pick a symbol that hasn't appeared yet in our work. Let's call that symbol, let's call it A. Okay. So that means all this must be equal to this. Okay. We have 3 poles. It's a third order system. It has 3 poles. We want, for a second order approximation, the second order approximation has a pair of poles like this, complex conjugate. And so there must be a third pole that we don't know. Let's go back to our root locus diagram. See, our root locus diagram says that we have 3 poles. You see, we have 3 loci. A pair of them will evolve along this set of curves. And there will be another one somewhere out here. So this one, we don't know where it is, but it corresponds to that factor. Okay. So let's clean up this part a little bit here, because I don't like to deal with complex numbers. And so this is the same thing. Do a little bit of algebra. This is the same thing as S plus 0.4 quantity squared plus 0.5 squared. Okay? That's these 2 factors taken all together. I used to say, at lunch, go to Chick-fil-A, grab yourself a sandwich, and convince yourself that this works. Okay? This is the real part. This is the imaginary part. But Chick-fil-A has been torn down, so you have to find some other place at lunch to go convince yourself, do this algebra, and make sure you understand this. Okay? So what that means is that this is a second order factor, and this is a first order factor. If I multiply these 2 together, it should be equal to this. Okay? So it's an algebra problem. So we want to basically say that our claim is that S plus 0.4 quantity squared plus 0.5 squared times S plus A. This is equal to this third order polynomial, S cubed plus 5S squared plus KS plus KZ. Okay. So the basic idea with algebra is just to multiply this out and then match terms. You know, you're going to have S cubed on this side, you have S cubed on this side. You're going to have something multiplying S squared, you have something over here. And you just go back and forth, and you see what K and Z need to be. Okay. Today, there's a lot of ways to skin a cat. There's a lot of ways to do algebra. I'll choose one way. There's no one way that's better. You choose your favorite algebra way. So one of the things that you could say is this thing should divide perfectly, because it's a factor, it should divide perfectly into this. Okay, this part should divide perfectly into that. Okay. clean this up a little bit. This factor is this s squared plus 0.8 s plus 0.4 squared is 0.16, 0.16, 0.25, 0.41. Okay, I'm just turning this into a second order polynomial. So this should divide perfectly into this. So let's do a little bit of algebra, and let's do that. All right. So what we're saying is that s squared plus 0.8s, s squared plus 0.8s plus 0.41, this is that second order factor, should divide perfectly into s cubed plus 5s squared plus ks plus kz. Okay, so now we're going to do long division. When did we learn long division? When did we first learn long division? Liar. Kindergarten. Education in America is going in the wrong direction. Kids need to be out playing more instead of in school.
So you realize you're an educator, right?
Yes. Which gives me the right to be critical of my own profession. Okay?
Aren't you an administered education since you...
That makes it even worse, right? That makes it even worse, right? I should. Yeah, okay. Okay, so we learned long division, they claim, in kindergarten. But we probably didn't look at it this way. We probably dealt with numbers. But the same principal idea occurs. So I have to ask myself, what do I have to multiply this thing by so I can get an s cubed here? What do I have to multiply this by so I can get an s cubed here? I'll need an s. Okay? So let's take this s now and multiply all this out. And I'll get s cubed plus 0.8 s squared plus 0.41 s. Okay, you see how that worked? I'm doing long division. I say, how many times can this go into this? Well, this is s squared. For it to go into this, there must be an s factor in there. So I said multiply by s, and I get s cubed, 0.8 s squared, 0.41 s. What's the next step in long division? Subtract. Okay, everybody's got their favorite way of subtracting. So now I get here 5 minus 0.8, I get 4.2 s squared plus k minus 0.41 quantity s. And bring down the next thing, plus kz. Okay, everybody see how that works? The next step is subtract. So the next thing I need to do is I say, what do I need to multiply this by to get 0.42 s squared? Not 0.42, 4.2 s squared. I need to put a 4.2 here. So now 4.2 multiplies this, and I get 4.2 s squared plus 0.8 times 4, let's say 16. Thank you, 3.36 s. And then I had to multiply 0.41 and 4.2. Okay. Now this is supposed to be perfect. So that means this times this must be equal to this. look earlier at our earlier algebra. We're claiming that this second order polynomial times a first order polynomial gives me a third order polynomial. We're claiming this second order polynomial times a first order polynomial gives me a perfect division, which means this should all be equal to 0. So now we know that this number must be this number. And in the root locus diagram, somewhere way at the beginning, we had thought there should be a pole between minus 5 and some place that we don't know the number yet. And right now it looks like that number is going to be 4.2. So all these things are coming together and they're reinforcing each other, which makes us feel good. This is supposed to be perfect, okay? So this is supposed to be all 0. So this is 0 plus 0 plus 0. So if that's the case, this must be equal to 0. So this is, therefore, I have two results. One of these is k minus 0.41 minus 3.36. That must be equal to 0. And the other is kz minus 1.722 is equal to 0. And once again, I have two equations and two unknowns. And we now try to pull out our kindergarten skills and try to figure out what these are. Okay, so let's do a little bit of algebra. From the first equation, I get k is equal to 3.77. Is that right? Now, and then I can plug that into here, and I get z is equal to 1.722 divided by k. Roughly a third. 0.45? Okay, I'm off. 0.45. Z is equal to 0.45. Okay. So we have solved the problem entirely by algebra. Let's take a look at our root locus diagram. It says that this number should be 0.45. Okay, so let's do the finished root locus. Real and imaginary. Here are the plant poles. Minus 0.45 minus 5. Okay? And now we know everything. We should be able to do a more accurate root locus now. Okay? We have two asymptotes. We have two asymptotes, and we're going to calculate what this location is, sigma. Sum of the poles minus the sum of the zeros divided by the number of asymptotes, which is 2. Okay. So if I add up all the poles, I get -5 and 0 and 0 minus the zeros, which is minus 0.45, divided by 2. That's about 5.5 over 2, roughly 2 3/4, roughly. So 2 3/4 is somewhere out here. I'm ballparking it, okay? So the root locus probably maybe looks something like this. And if we've done things right, then here's S star, -0.4 plus J 0.5. Now, we got a few minutes. Let's suppose you were to go and put this into, you say, does this really work? One of the things we'll do as an engineer is let's simulate the behavior. And so we're going to say our plant G is a transfer function. The numerator is 1, and the denominator is s squared. So this is the satellite. Okay? And then we have a compensator. The compensator is a transfer function. K was, let's see, what was K? K was 3.77. So I have 3.77 times s plus 0.5, 0.45. I think that's what z was, right? Z was 0.45. And then the pole of the compensator was s plus 5. Okay. So the combination of these two, I'll call it CG. CG is the series combination of C and G. So this is the phase lead. This is the satellite. This is the phase lead. This is the open loop. Let's calculate the closed loop. Let's give that closed loop a name. Let's call it H. H is the feedback system, where the forward gain is CG and the feedback gain is 1. So this is theta of S divided by theta R of S. Okay. This is closed loop. And then what we're going to do next is we'll say, do me a step response of H. Now, you will probably see something like this. Okay. Let's go all the way back here. Let's figure out where it's going to settle out, okay? Let's take a look at this control system, review something from maybe the second, I think it was the second test. Here's a control system. It's third order, because it's second order and first order, it's third order. What is its system type? It's type 2. And then we say steady state error. If I have a step input, what will be this error if I have a type 2 system? 0. So that means this will equal to that. So if I put in a 1, if I put in a unit step here, this should settle out, and so this will be perfect. This will be equal to theta r, whatever theta r will be. And it should settle out in 10 time units. But what you're probably going to find is that this overshoot will very likely be greater than 10%. It will very likely be greater than 10%. Why is overshoot greater than 10%? We designed to be 10% or less, and we got, we didn't get that. Well, we have to remember that theta O of S over theta R of S, if we write this transfer function again, let's bring it back out. We calculated on an earlier page, is going to be S cubed plus 5S squared plus KS, which is, K is 3.77, is that what it was? K is 3.77S, and then K times Z, or whatever that is, K times Z, and then up on top we have 3.77 times S plus 0.45. Okay. So there's a couple of things that we should recognize now. This is third order. It's third order, but our equations that we use for design were second order. So there's one engineering error there. Okay, we're using second order, third order, but design equations assume second order. The other thing that you will notice is our second order equations assume there is no zero up in the top. There is no zero up in the top. Okay. So there's also the other thing is there's a zero. And that is not in our second order approximations either. So let's talk a little bit about the zero and say what is the effect of having this S in the numerator. So S is in the numerator, so it's like multiplying by S. Multiplying by S in the Laplace transform domain is equivalent to doing what in time domain. Multiply by S is the same thing as what calculus operation? Derivative. So our response is going to be not just this, but it's going to add plus a derivative component. It's going to add some more rate to it. And so that means our response is not just going to be the normal response, but it's going to have some added rate. It's going to add some added speed, which means it's going to tend to be higher overshoot. All right, so we're going to end up seeing in simulation that our overshoot is going to be greater than 10%. Okay? Now, your boss is going to say, wait a minute, I'm paying you $55,000 a year to design this, and you didn't give me 10%. What are you going to say? You're going to say, I'll give you your money back?
No, give me more.
You say, give me more money? He says, you're on salary. There's no such thing as overtime. So you just work more. What can we do? Given the fact that we know that we're using second order equations to try to do a high order problem, we know that our form of equation doesn't really fit the standard order model. What can we do? What would you say? Anybody got a suggestion? Clearly we have to redesign it. We've got to go back to the drawing board. What might we change when we go back to the drawing board? Any suggestions?
We dropped our 10% down on our design.
Okay, somebody suggested instead of designing for 10%, which is what the guy asked for, you might say, okay, he asked for 10%. It's a complicated problem. I probably maybe ought to hedge my bets a little bit and maybe design for 5%. Okay, the boss doesn't need to know that, but that's what I'm going to do. I'm going to design for 5%, and then hope and pray that it ends up getting me 10%. Okay, so these are things this is where engineering starts hitting the road. Okay, the rest of the stuff is just science, but engineering requires us to make some judgments. We're going to have to do that. So maybe what we can do is in redesign. Maybe aim for 5% overshoot. Maybe aim for 8 seconds settling. Okay? These are all maybes. What else could improve damping. Maybe we could add a phase lead, another phase, a second one. Add another phase lead, because that phase lead will, increase phase margin. And more phase margin means I have less, I have more anticipation. I should maybe reduce the overshoot. So I may have to go back and say my compensator is not just this, but I'm going to add another block in there. Okay, you may need to be thinking about this on your design project. Okay, your design project is a fourth order system. And for most of you, you probably are not going to be able to get all the way there with any of the compensators we've talked about in class. Unless your name is really short. Okay, any of you have long names with a lot of syllables, I think you're going to have a tough time getting there with just a single phase lead or something like that. You may have to say, if one gets me part way there, maybe I need to try two. So you have to play with that a little bit. All right, I see my time's up. Let's go ahead and call it a day. We have a test on Friday. For long names?
I did a single phase lead, and it took me, I just randomly guessed at parameters, and within one try, I got the right answer.
What's your name?
And Nicholas Alexander Jones.
Are you sure you did it right? So you think a long name is easier? I think a long name is going to be harder.
I don't know if it's easier,